works for me.
Andrew, back up some. You're disrupting my field of view.
So we're going to be considering RLC circuits. And as the name implies, they are circuits that contain resistors, inductors, and capacitors in any order. The order in which they occur, as long as they're all in series, does not matter.
If there's more than one, does it get screwed up?
If there's more than one, then they simply add according to the series and
It just becomes the
right, the
equivalent
series
circuit.
equivalent. Yeah, that's exactly right. Inductors in series, by the way, simply add. L1 plus L2.
Should ask that.
Yeah.
All the time now?
If we have a missing element, for example, if I just have an R and a C, then L equals 0 for the purpose of that circuit. There's no problem.
Why would that be?
Because it's
Because there's
nothingness.
no inductor. So you have 0 inductance.
So what you're saying is basically all circles, all circuits are RLC circuits, except some just.
All circuits with these components are all RLC circuits.
But
Yes.
if they don't have it, then it just equals 0.
No, then the component equals 0.
But there are other components in life besides these three.
Oh.
Transistors, diodes.
Oh, okay, so yeah.
Stuff like that.
Okay, so
But if it does
hypothetically, if it didn't have a resistor, the resistor would be 0.
Yeah,
And
exactly.
you just put in like a makeshift, like in synthetic division. If a term's not there, you put in like a 0.
Yeah.
So,
Okay.
so if it just has a resistor, it just has an inductor, it just has a capacitor, they can still be RLC circuits, or just.
Yeah, the theory that I'm about to explain is very general. You
Okay.
could substitute zeros as appropriate. All right, so we already know that each of these has an impedance.
And like, what's impedance? Like for clarification, like
Impedance is the generalized concept, the generalized idea of resistance. So notice that the impedance of a resistor is just its resistance. But the impedance of the inductor and capacitor are very interesting because they are frequency dependent. Specifically, and students sometimes get these confused, remember that the impedance of an inductor is going to be large when the frequency is large because the inductor does not like quickly changing currents.
That's its job.
That's its job. And the impedance of a capacitor is going to be large when the frequency is small because when the frequency is small, that gives the capacitor plenty of time to charge up. And as a result, it resists.
When we were doing capacitors, you said they charge instantaneously. Is that just like it's instantaneous to humans, but
It's not actually
instantaneous,
but.
So yes, that's the right way to think about it. We skipped the whole RC circuit thing. But had we done the RC circuit thing, what we would have discovered is that when you have a circuit with a resistor and a capacitor in it, then it takes a certain amount of time to charge up. And that time depends upon the value of the capacitor. Obviously, larger capacitors take longer to charge. It also depends upon the value of the resistor because in order to charge, you have to draw current.
That's okay. I have a question.
Wait. Now, if you have a circuit with just a capacitor in it, you still have a little bit of resistance because of the wire. 10 to the minus 5th ohms, something like that. So you're going to have a really, really small time constant that's basically negligible. By the time your thumb comes away from the power supply switch, it's already charged. Now your question.
Oh, so when he said it was almost instantaneous, is it kind of like where we were talking about it's almost like this, but there's actually just like a really, really steep slope right
Yeah,
there?
that's exactly it. But notice there is a difference between that kind of circuit and what we're talking about here, and that difference is the power supply.
Yeah.
In the circuit you were talking about and we were talking about earlier, we had a DC power supply, so all we were going to do is to go up to our max voltage and be done. Now we're looking at a sinusoidally changing power supply that's going to push and pull current through that circuit, and so we're looking, these equations right here are applicable to a changing.
won't the inductors kind of balance it out? Because it's,
Yes, they will kind of balance it out. That's exactly right. So that's why there's an impedance for the inductor that depends upon the frequency. The higher the frequency, the more balancing essentially occurs. Okay. But there's one more piece of the puzzle that I haven't told you about. And unfortunately, to give you that whole piece of the puzzle, I would have to do some calculus with imaginary numbers. We're not going to.
So I got 2. 3.
So,
So Christine.
instead,
She didn't got 2.
I'm just going to give you the results. And that is this, that when you have a resistor, we can think of that resistor's impedance as being a vector whose magnitude is R and whose direction is 0 degrees in the plane. Now, the 0 degrees is going to correspond to something real in just a minute. But right now, we're just thinking this is a mathematical model.
It's imaginary.
Yeah, well, specifically this one. We're going to think of the inductor as having an impedance that is 2 pi FL, but it is going to be directed plus 90 degrees, and we call that the phase shift of the inductor. And the phase shift of the inductor is going to be plus 90 degrees. And what that really means is that if I have just a circuit with an inductor, then the current is going to be 90 degrees out of phase with the voltage. And that's because of the lag, because of the inductance. Meanwhile, we're going to think of the impedance of the capacitor as being 1 over 2 pi FC, and it's going to be directed minus 90 degrees or plus 270 degrees, whichever way you want to think about it. So that the current is going to be 90 degrees, 90 degrees backwards. So it's going to be that way. Plus 90 is like so, minus 90 is like so. Now, what happens when I combine them all together? When I combine them all together, all of these impedances are going to add like vectors.
That way.
So I'm
Mhm.
confused of why it's plus 270 minus 90. Why isn't it just plus
It's
20?
or.
These are coterminal angles. Whereas
Oh,
plus
okay.
270.
Starting from there. I was
Yeah.
thinking from the 90 degree, and I'm like,
Hmm.
what? No, I thought you were adding 270 and then subtracting 90. I'm like, that's kind of pointless.
Yeah, no, this is the minus 90 degree angle here, that's the plus 90 degree angle here. And this one has no phase shift, that's 0 degrees.
Okay, that makes sense. Can you do this in terms of radians?
Yes, but it's almost universally done in terms of degrees.
Why are some things done in terms of radians and something?
So radians are so much easier to work
They
with.
are, but it's just why.
Well,
why is
No, it's a really good question.
Use
It's the
radians.
Babylonians' fault, really.
Those jerks.
They just believed that 6 was a magic number, and there it is.
Why couldn't they just believe that pi is a magic number?
That's an interesting question.
They probably haven't figured it out yet. Have they?
They're geniuses. They built the hanging gardens, for goodness gracious.
You're about to get me off into a math tangent. I'm just not going to go there.
Wait, just one question. Had they figured out pi at that point? As far as we know?
Pi was known to about 2 or 3 places. Pi was known to be about 22/7.
They're pretty much
By the Greeks. Now the Greeks are roughly contemporary with the Babylonians, but I'm not sure if the time periods exactly match up. The height of the Babylonian Empire is right around 550 BC or so. The Babylonian deportation of Israel is like 73, I think that's right.
How'd you do this?
because
And went to
what's the place called?
College?
yeah,
College.
yeah, that's what the place is called. Yeah, let's move along.
Okay.
And anyway, Homer is like 900, and the Greeks, like Alexander the Great, takes over in the couple of centuries before Christ. All right. Okay. So how do these all combine? They're going to combine like vectors, so that if I have ZR and I have ZL and I have ZC, then I'm going to add them like vectors. There's only one component that is in the horizontal direction, and that's ZR. And its value is R. And I have 2 components in the Y direction, and those are ZL going up and ZC going down.
So they just add
just about, except that ZC is going down, so they actually subtract.
We,
Wait, well, if it's plus 270, then would it add?
Mm-hmm.
I mean, would it subtract?
Take
Instead of-
direction. Which way is it going?
It's going down.
All right.
It's, okay, just subtract. Okay.
It's going down. The plus 270 right here refers to a counterclockwise angle measurement, right?
Mhm.
Minus 90 is a clockwise angle measurement. So for angles, plus and minus have this units of counterclockwise, clockwise.
Yeah.
For x and y components,
Mhm.
plus and minus have a different significance.
Okay.
For x, plus means to the right, y means to the left. And for y, plus means up and minus means down.
It's just one of those things.
Yeah, just one of those things. Okay, so now when I compute the magnitude of it, the magnitude of z is going to be the magnitude of that vector as computed by Pythagorean theorem, which we know and love. It's going to be the square root of the x squared, oh, not minus, plus the ZL minus ZC squared. So it's just Pythagorean theorem. Now this is significant for us because it's going to tell us some things. First of all, it's going to tell us immediately that we're going to have the smallest impedance when ZL is equal to ZC. Think about that for just a minute.
0 squared.
Right. That's when this term will be 0 and I get just off. Now the reason that we can adjust those is that we can change the frequency, and ZL and ZC depend upon the frequency. So we'll take a minute to explore this because this is a really interesting issue later on. But first we'll do an example. And then the second thing that's going to happen is that there's going to be a phase shift. And we're going to represent that phase shift with lowercase Greek f or phi, the phase shift. And that's going to be the phase, or the angle of that vector right there, which is a familiar formula to you, inverse tangent of y over x, which we're going to spell like that.
I remember that from something. I don't remember what.
It's the conversion.
It is. Yeah.
Yeah.
Yeah, rectangular polar.
Yes.
Yeah, that's right. Inverse tangent of y over x. Okay. Do not memorize these equations. We're doing this in a conceptual fashion today, and that's okay. But I want to go somewhere with these. And the first place that I want to go is to examine an RC circuit. I have here an RC circuit constructed for us. And the resistor has a resistance of 1200 ohms.
and by RC, it doesn't have an L in it.
That's correct. It has no L, so we're going to take L equals 0 for all of this. It also has a capacitor, and I need to check the value of the capacitor. Hang on a second. Okay, yeah, so the value printed here is 68 times 10 to the minus 9 farads for the capacitors on this guy. All right, so that's our circuit. And now what we're going to do is first we're going to compute, and then we're going to compare qualitatively some results from our formulas for the impedance against various frequencies. Now what we are capable of doing here is a wide range of frequencies. We can go all the way down to 1 hertz. Actually, we can go down to 0.1 hertz, and we can go up as far as 1 million hertz. So there's a huge, huge range of frequencies, and we're going to check for that. Or at least many of them.
Every single one. Every single hertz.
So let's actually start at 100 hertz. And we're going to go up in factors of 10, all the way up to 1 million. How about I just do scientific notation? Wouldn't that make a lot more sense?
It would.
Well, it's
And we'll compute the ZR, which is equal to just the resistance. So that is 1,200 ohms for every single frequency that we pick. That's the virtue of resistors, is that their impedance is a constant number. But for the capacitor, we're going to use 1 over 2 pi fc as our value here. And so now we've got to do a little bit of computation. Everybody grab your calculators and compute the impedance of the capacitor with a frequency of 10 to the 2 and a capacitance value of 68 times 10 to the minus 9. Go. So I'm getting ZC is equal to 23,400 ohms. Now, what I want you to observe about this is that the ZR is substantially less than the ZC.
Well, but it don't always when you get up to higher numbers.
That's right. As we continue up into higher numbers, this number is going to drop here, and we're going to start to see a change. All right?
Wait, do you want to know that?
We'll get there. So the Z total then is equal to root R squared plus ZL minus ZC squared. And of course, what is ZL in the circuit?
Zero.
Zero, right? So what we're going to do then is just this plus, this squared plus that squared, square root. And what you have probably discovered in your physics career is that when you have a right triangle with a really long leg and a really short leg, the length of the hypotenuse is going to be basically the long leg. So when I square this and I add 1,200 squared and take the square root, look at that. I get 23,436, which is not that different from the ZC itself. In other words, at this frequency, the capacitor is completely dominating the entire circuit.
And we know that because of the.
By comparing these two numbers here. But let's do one more thing. Let's calculate the phase angle, which is equal to the inverse.
I'm running out of room.
I know, me too. Is the phase angle, which is the inverse tangent of ZL minus ZC over R, or ZR. And when I plug that in for this guy right here, and make sure that you are in degree mode and not, then I get negative 87 degrees. Now, keep in mind that the phase shift for a pure capacitor is minus 90 degrees.
So it's like 3 degrees off.
Right. So in other words, basically the capacitor is completely taken over in this particular circuit. Now let's actually see that happen here on the scope. Uh-huh.
Did you know in the future to get this? It says published fall.
All right. So what I have are two different channels going on at once. And one channel is going to measure.
Wow, my ears.
What?
My ears just are like rumbling.
Probably got fluid stuck in them, Ben. There, it's the way it was. Yeah, bus.
Peter, what amazingly squirrely.
Bus. Well, we had a lot of ice cream.
Okay. How come I'm not getting anything? I got something. Oh, I see why. Okay. So what I'm doing is I am measuring on one channel the why am I getting nothing here? I should be getting something solid.
Shall I post the recording?
Yeah, why don't you pause it for just a second while we... Okay, so yeah, so what was happening was we actually weren't seeing it because the two signals were on top of each other. So if I go to 100 hertz now, and I put this on a time scale so that you can actually see it, like so. See if we can get it to lock in. No, it's not going to lock in very well. It does pretty well. All right, I want you to observe the following things. The first is that the voltage across the resistor is basically 0. That's this channel 2 that we're seeing right here. And if I look at just channel 2, I'm getting nothing across the resistor. Since V equals IR, that means I'm getting very little current. Why am I getting very little current? Because the impedance of the capacitor is so large. And then the second thing that I want you to observe is the phase shift that's going on. Look at where the peak is on the original signal here. Now look at where the peak is on the output signal, which is right there. And that peak, let me amplify the output signal a little bit so you can see it. There.
Can it like not be as like seizure-y?
Yeah, sorry, it can't. Notice that the peaks are shifted. This peak is shifted backwards, and that backward shift right there reflects a 90-degree, it's really an 87-degree phase shift, as we predicted. Okay. All right, now let's do another computation.
And seizures. Oscillations are not like people with epilepsy.
Yeah. Oh my god, that would be really bad.
Well,
That's really cool.
That's actually pretty cool.
There. That'll do. All right. So now let's consider what happens when we do 10 to the third hertz instead of 10 to the second. What changes here? I think we can do this efficiently. How are things going to change if I multiply my frequency by 10?
It's going to
Like decrease by 10?
By a factor of 10, that's right. So it would be what number? 2340. Now, you'll notice that 2340 is starting to be in the same ballpark as the 1200 right here, right? Same order of magnitude. And so when I actually compute the magnitude of Z, I'm going to get a number that is going to reflect the contributions of both of those.
So then the other one is it 23.4 for the next one down for 10 to the fourth?
234, yeah.
Oh. Oh, yeah.
So yeah, 1200 squared plus 2340 squared gives me that square root, and I get 2630, which is still closer to the impedance of the capacitor, but it shows much more of an effect of the resistor right there. And that effect is also reflected in the phase angle when I compute the phase angle of the inverse tangent of 2340 over 1200, not forgetting my negative sign. I get negative 63 degrees. In other words, my phase angle is starting to moderate. All right, so let's see that with our oscilloscope here. I'm going to change my frequency to 1000. And now when I compare these two and put them on the same scale, like that, then you can see the effect. The voltage drop across the resistor is a whole lot larger than it was at 100 hertz. Everybody see that? Mm-hmm. And not only so, but also this phase shift is starting to head towards 0. The peak of this wave is starting to line up under the peak of that wave. Right, the local max. Okay, well, let's go one more round here. If I increase my frequency by a factor of 10 again, now I get 234. And now the amplitude or the magnitude of my impedance is going to be pretty close to just 1200. In fact, it's 1223. And when I compute the phase angle, I get a mere negative 11 degrees. Compare that to the phase angle of just a pure resistor, which is 0 degrees, and you can see we're a lot closer to the resistor. So what's happened here is we have transitioned from a circuit where the capacitor has dominated now to a circuit where the resistor has dominated.
Why does it do that?
Because as we increase the frequency, the impedance of the capacitor goes down, down, down. And the impedance of the resistor doesn't change.
So it's,
Let's actually see that in the circuit over here. If I put this now on 10,000, and I compare the two,
You get Kit talking to you.
you can see the two different waves, especially if I move one of them up a little bit. So you can see the two different waves, but you can also see that they're almost identical. You can see just a little difference between them right there. That's an 11-degree phase angle right there. And you can also see that the amplitude of the magnitude of the voltage across the resistor is basically the same as the magnitude of the voltage across of the signal. And if I go one more, to 10 to the 5th, now this guy drops to 23, which is a spit in the bucket. That's a rounding.
23.4.
Yeah.
Sig figs.
Which is a rounding error compared to the resistor right here, right? And so when I actually compute, it will come as no surprise to you.
Here's the other ones. You've been 23,000, 2,300.
Then I get 1,200 right there. And when I compute the phase angle,
Actually, Mr. Cook, wouldn't it even be less than that because the F is rounded to 1, so making it bigger.
Close enough for government work there.
sorry, I wasn't quite catching that.
When those numbers be 20,000, 2,220, because the F is to one significant figure.
Oh yeah, you could do that. Yes.
She's like,
And
significant figures.
we see that here in this circuit.
Oh, thanks for the clap.
She's the only one.
No, that was bad.
No, not even.
Yeah, well,
She's the only one. Same thing.
Not even her. You can't actually see the difference between the two signals.
Even if you shove up the.
They're identical. Until, ta-da,
What?
look, there's really two. But actually, they line up. They're practically identical.
it looks like.
Why?
Hold on.
Because the impedance of the resistor is so large that the voltage is dropping all across the resistor. And we're getting nothing across the capacitor at all.
Can you zoom in on it? Like,
Zoom in.
so it's not as many waves,
Yeah.
but they're
What's the
different.
aspects of a human being?
Well, right. One's input, one's output. But look how close they are.
What do you mean one's input, one's output?
So one of them is directly the voltage of the signal generator that's being put out by the function generator right here. And the other, the output, is the voltage drop across the resistor. And at this frequency, because the impedance of the resistor is so large compared to the capacitor, the voltage is dropping all across the resistor
That's cool.
and none across the capacitor.
So like, it's like the capacitor doesn't exist.
Exactly. That 23 ohms right there might as well be zero.
For Mr. Kettle, that thing doesn't pick up sound waves also, does it?
If you have a microphone. Yeah. So one of the things that I have done in years past is to bring in my guitar and hook this up directly. You can see the sound waves on the guitar.
We have a 4-inch cable downstairs that I have access to. I'm sure Silas, we forgot that it's Mr. White for her.
Well,
That's
so
important.
we don't even see anything right here. This is going to be basically 0 degrees. This is a pure resistance circuit.
Future Andrew, remind yourself to ask Mrs. Durant for her album. This is for Mr. Gate.
Shut up. You think you're gonna watch this? I agree with this.
No, it's funny that you said that on the recording.
Okay, so here's what I want to observe. And that is that if we do a diagram of VR over V, which we might call the gain of our circuit, and we do that as a function of frequency. Now I'm going to do the frequencies in a funny way. I'm going to do a logarithmic plot. Instead of doing a linear scale, I'm going to plot it linearly with respect to exponents. Then what we get is, in this region, where the capacitor is really active, we get very little voltage across our resistor. But now all of a sudden, when we hit the sweet spot, the resonant frequency, then all of a sudden our response increases greatly and we swing through to a maximum gain of 1 right there. We call this kind of a circuit a high pass filter. It is going to pass high frequencies through, and it is going to weed out the low frequencies.
So this is the high mid and high on the soundboard, right?
That's exactly what it is. They are literally made with capacitors and inductors, or the digital equivalents of those anymore. And actually, honestly, they use a trick to use just capacitors and analog ones because inductors are kind of big and bulky. Capacitors are more convenient.
So that's a 1.
That's a 1 because the greatest voltage I could possibly get out of this is the input voltage.
Wait,
Unless I have some kind of amplifier.
wait, what did you say was big and bulky?
Inductors are big and bulky.
What do they look like?
Coils of wire wrapped around iron cores.
So pretty
Like
much just
that
like a
kind of
computer block.
Huh?
No, I'm thinking like super magnet kind of thing.
No,
No,
Like-
You could. Uh-huh.
No,
All right, so
that's
one more
fine.
thing that I promised I would talk about, and that is resonant frequencies.
Oh.
We'll go all the way back to the observation that we made,
I got these uniforms.
and that is that the impedance is the smallest when ZL is equal to ZC. So I want to take that and just do the math on it. Let's say I have an RLC circuit. And what I'd like to do is I'd like to tune it to find the frequency that gives the smallest impedance. In other words, it lets the most power through. Well, we've already observed that that's going to happen when ZL is equal to ZC, because that's when the impedance, which is root R squared plus ZL minus ZC squared, is going to be the smallest. And we have a formula for ZL, that's 2 pi FL. And we have a formula for ZC, which is 1 over 2 pi FC. And so if we're trying to solve for F, then it would make sense to multiply both sides by F, to divide both sides by 2 pi, and to divide both sides by L. And so now we have an equation for F, and we take the square root of it, keeping in mind the frequencies can't be negative. Then we get the resonant frequency, which is 1 over 2 pi root LC. And so what kind of circuit is this when I have an RLC circuit? Well, here's what this does.
Wait, why did it become F?
Frequency,
Yeah, why did it become frequency?
because you put them equal to each other.
Wait, where are you talking about?
She's curious. She's wondering
Which
how
one?
you derive
Why? Oh, wait. Okay.
different equations.
Never mind. I see.
Okay. So,
Wait, why'd you square it though?
Because that's how they equate.
multiply both sides by F.
No.
So if I do again a frequency plot to get the amount of gain in my circuit, what I'm going to find is that the maximum gain, which is the voltage across the resistor, is going to be found when I hit the resonant frequency, which is 1 over 2 pi root LC. So this,
You're talking about like glass, that would be what I was talking about.
yes, it's a very similar idea,
And that's like feedback.
and like feedback.
So, how loud would the resonant frequency be if you got like exactly the resonant frequency to break glass?
Frequency is not loudness, frequency is pitch.
It's like magnitude.
So you could just do it like ever so quiet.
You could do it quietly and build up a fair amount of energy. It has to be a certain amplitude in order to actually have an effect to be able to break it. And the frequency that you need is actually going to depend upon the shape and thickness of the glass.
So like, what if it was a cup? Like
It
a cup.
depends on the shape.
Right.
So
And of course, you could always do it like in Harry Potter, just kind of sing it and smash it against the wall.
I do remember that.
Amazing!
I'm amazing.
All right.
Wait, you never saw Harry Potter, Alexis?
Yes, I did.
All right, well, that's it for today.
I've seen Harry Potter.